And so we'll do that close. Just Google Husky bites Michigan Tech. You have to add Michigan Tech, otherwise you're going to come up with images of huskies biting children's hand off. And I've never seen a husky be aggressive, but you got to put in the Michigan Tech part. Because you can catch up with the webinar series that way. And so I think we're getting close to the hour. Looks like we have 39 attendees so far, and that is awesome. I'm seeing some names I recognize, and that's awesome to see our alumni here. And usually we do a poll to ask how many people here are alumni and how many people here are students, but it's typically folded out to be about 1/3 alumni, about 1/3 students, and about 1/3 kind of everybody else, which is mostly, well, definitely including our Michigan Tech community. And so it really is awesome for you all to be joining us. And so if you haven't joined us before, I'm Janet Callahan. I'm Dean of the College of Engineering. And it is, we decided to offer this series this summer because we needed a little mental relief, honestly, from the really serious things that were happening in the pandemic. And of course, now even more serious things have been happening, which it's kind of really shifted my equilibrium a little bit, honestly. I've got a son in Chicago and kind of worried about him. He's right in that area where a lot of violence is occurring. So Paul Dewitt has posted a good comment that my peroxide formula for deskunking my dog works well for other purposes, removing smells from carpeting. So we're on the hour, Brian. Why don't we go to the next slide? So I wanted to begin with a moment of recognition and silence. And I wanted to read a message from President Rick Kobach, who sent this out yesterday to the Michigan Tech community. And so I would like to quote him. This is from President Rick Kobach. "I grieve for George Floyd along with his family, his friends, and our entire nation. His death was egregious. As we navigate these challenging times together, let us serve as role models for unity and strength. Let us use our voices, our skills, and our influence to advocate for change. And let us elevate the level of public discourse around equity and inclusivity. The responsibility of justice rests on us all and can only be carried out as one community built upon a plurality of voices. Please know that we are here for you and our hearts are with everyone hurting across the nation and here at home." And with that, I end quote. Next slide, please. All right, and this is to cue me to let you know that if you should fall out of Zoom, sometimes we have to lock it. Please know that you can follow us on Facebook live stream, and so you can use that little link there, or you can just get into your Facebook and Google College of Engineering, where it is being live streamed. So So I want to make sure I thank the webinar team, and the responsibility is shifting from Stefan to Bryant, and Stefan's making sure we don't have a mishap tonight, but Bryant is now taking over the lead on webinar. So thank you so much, Bryant. Thank you, Kim and Sue, for being there in the background. I want to make a quick plug. If we have any future students out there, and this future students means anybody, I would say, from kind of middle school on up, we're going to have a Track B summer course starting July 9th on a Tuesday, or Thursday actually, and then 5 sessions in total, toggling between Tuesdays and Thursdays. We're calling it three chairs and a dean, tips and tricks. And we're going to be sharing some of the things we really wished we would have known before we started college relative to kind of learning technical content. And I will have instructions on how to sign up for that next week in the webinar. All right, and with that, I'd like to introduce our speaker tonight, Dr. Rebecca Ong, who is our Michigan Tech University expert on bioenergy production, among other things. She has done work on sustainable foam made from renewable lignocellulosic biomass. And Dr. Ong, like most of the Michigan Tech family, engages undergraduate students in research in her laboratory. And you could just Google her just to read some stories from some of her students. And so tonight, we're going to be hearing from Rebecca, and you can see some of her bio. She started off here at Michigan Tech, went on to get it with dual degrees, chemical engineering and biological sciences, and then went on to get her PhD elsewhere. And then we were able to recruit her back. And so we're so happy to have her here as a faculty member in the Department of Chemical Engineering. And so with that, I'm going to turn it over to you, Dr. Ong.
Okay, thank you, Janet. Let's see if I can share my screen. So I'm gonna try something a little different. We'll see if it'll work. I gotta go and start it on my phone, so I'll be right back. Oops. Come on.
Rebecca is doing an interactive webinar where she's going to be actually doing an experiment during the webinar. And so she has an assistant with her who is going to be helping her. And she's arranged cameras around her kitchen so that she can do this experiment and we can participate.
Sorry, I'm having some technical difficulties.
No, that's okay. 2 weeks ago, Brad King, he was parked out by a waterfall and he kept going in and out. It was kind of a problem for a little while there, but
I can just hold the camera.
So
let's see if I can get it closer. That'll help. Stop, please.
Are you back? There you are.
Sorry, give me 1 second. We'll see if I can get this to work. It's not reading, it's not working on my phone.
Do you want Brian to show your slides?
I don't need my slides, I need them.
Okay.
If not, what I'll do is I think, I had it all set up to do this and I think it's not gonna work. So
No, take your time, take your time. We're patient. So Brian, tell us a little bit more about where you went when you were over the weekend on Sunday when the weather was nice.
So some of you, if you're an alumni of Michigan Tech, you might have gone to the mouth of the Montreal, or some people call it Montreal Falls, which is about 7 miles northeast of Bay Degree Beach towards Mount Bohemia. And so it's down a 2-track road called Smith's Fishery Road. And there's a nice waterfall that plunges into Lake Superior, and it was a beautiful day. And the wind was cooperative in that it kept the bugs away. So it was a nice busy day.
That is always a good thing.
All right, I give up on that. So it did work. I did try it this weekend and it worked, but it's not gonna work now. So what we're gonna do, I think, is just start with the experiment. So today we're gonna talk a little bit about 3 of my loves. Chemical engineering, plants, and microbes. And I use all of them in my research. And what we're gonna do today is we're gonna do 2 experiments that all of you can do at home. And I'm hoping some of you actually downloaded the protocol and the supplies list and are able to follow along a little bit at home. we're gonna be skipping some steps. This is my assistant, Penny. She's 4. She loves these experiments. She thinks they're fun, right? You're gonna be quiet now. And so you can feel free to follow on, but I'm skipping some steps just in the interest of time. So you might not be able to keep up. That's okay. You can always finish them on your own later. So we're actually going to start off with the second experiment, and that's because it takes a little bit of time to work. And so usually you won't see any results for about 30 minutes to an hour, which is a lot longer than what we have. So what I have here are some clear plastic bottles. I don't actually drink bottled water, so I bought these specifically for the experiment. So you can just take any used bottles that you have. Ideally, you want something that's colorless and clear, so you can see what's going on inside of the bottle. You don't have to if you don't care, but it's interesting to see what's happening. So what I've added to most of these bottles are 2 teaspoons of yeast, just the yeast that you get at the store that you use to make bread, and 2 teaspoons of sugar. And so I have 6 bottles here. And what we're doing is an experiment to test how yeast responds to acid. And so I didn't actually know it was going to happen. I designed this, and we do that when we design experiments, right? We propose a hypothesis. We are like, we think this is what's going to happen, and then you test it. And so what I have here, let go my arm, please, is I have 3 different liquids. I have just plain tap water that's been warmed up, so it's a little bit warm. You don't want it super hot or you're gonna kill your yeast, so make sure it's not boiling. You just want it sort of lukewarm. If you touch it, it should feel warm, but it shouldn't hurt you. Then I've got some lukewarm apple cider vinegar. I used apple cider vinegar because I was worried about running out of white vinegar, and also it's nice because you can see the color difference. And then this one is half apple cider vinegar and half water. And I wasn't really sure what's gonna happen. But based on what I know about yeast, I don't think it's going to like the acid very much in the vinegar. And so what we're going to do is actually test this and pour some of these liquids into our containers. But first I need to add some yeast and some sugar to my last bottle. If you have a funnel at home, you can use that. I didn't have one that was small enough opening, so I made one out of paper. It's really easy to do. You just roll it into a cone, make sure your opening is small enough to fit into the neck of your bottle, and then you hold it in place, and then you can add your ingredients. So I'm gonna add 2 teaspoons of sugar. And you're gonna wanna do this for every single bottle because this is gonna be constant across all of them. And then I've got my bread yeast, and I'm gonna add 2 teaspoons of yeast. And you might notice that I only have 3 liquids, but I have 6 bottles, and that's because replication is extremely important when we're doing scientific experiments. Because you might say, oh, it worked once. Well, that's great, but how do you know it wasn't a fluke? Maybe you added too much sugar and it worked really well. Maybe you forgot to add the yeast and you didn't see any results. So replicating is extremely important when we're doing scientific experiments. So what we're gonna do is just add 1 cup of liquid to each of these bottles. And so I've got water here. Try to not spill any because you sort of want to have an equal amount of liquid in each of these containers. All right, and then once you've added that yeast, it likes to stay at the bottom, and so you can shake it up a little bit. My bottles are not very good quality, so they tend to leak, so be a little careful. Now what we want to do is we want to add a balloon to the top, and I'm using balloons that match the liquid, and so water is going to be a yellow balloon, and I'm going to put that on each one. And then I'm going to repeat that for each of these. And I think we'll just do a couple more, and then I'm just gonna skip because I actually already did this in advance. So we'll add some more. So this is the apple cider vinegar. We'll add 1 cup to our bottle.
So Rebecca, you must have been an early buyer of yeast because I tried to get some a couple weeks ago. There's none in any store in Houghton.
You buy it in bulk, and I forgot to mix this one. We buy it in bulk, so we have this huge container from Costco that we order in. And so that's what we use. And so we have a huge amount actually in stock. All right, so you're gonna wanna repeat that for every single liquid. So my green is gonna be my vinegar, and my orange is gonna be my half and half. And then we're gonna set those aside for, I don't know, half an hour to an hour, and we're gonna see what happens. So I already started some. And so we'll be able to come back to that in Magic TV time and look at the results of our experiment, and we'll see what happened. And we put orange balloons on the half and half mixture. All right, so I'll just set these aside. Yeah, you've got an orange one. We aren't filling that one though. All right, so.
Can I have this one?
Afterwards. So we're gonna talk a little bit about what's actually happening in this experiment after we look at the results. All right, the next thing we're gonna do is make some color changing potions. And I really love this experiment. This is so
excited about this part.
So I did this earlier this summer. You can do it with red cabbage, which is the most famous one. Or you can do it with any vegetable that's kind of purple in color. So if you really wanted to waste blueberries this way, you could use blueberries. I had purple carrots from my garden. Use those as well. They don't have quite as nice a result. The compound that's in them that makes this work is a little bit different. But we're gonna use red cabbage because it makes the most vibrant colors. So what you're gonna want, you don't want the whole cabbage. You actually need about 1/8. So being careful, cut off about a wedge of your cabbage. You can set the rest aside. And then we're gonna cut these just in pieces. And then we're gonna stick it in our blender. And you don't have to be exact. All right, so we've got that in our blender. Then you want some hot water, and I've already heated this up, and you're gonna add 2 cups roughly of hot water to your blender. All right, put the lid on.
How hot?
Get it boiling, put it in your tea kettle, and then you can pour it in. It doesn't, some people, some of the protocols say you can boil this on the stove. It's not necessary. The less water you have, the more concentrated it's gonna be, which could have impacts on one of the things we're gonna do at the end. But I think 2 cups is of water is pretty good. So we're gonna turn it on. Make a lot of noise. And it doesn't take very long, it's all blended up. All right, then you want a strainer because you don't want all the cabbage particles, the pulp, ending up in your liquid. And so we're just gonna drain that out.
It's purple.
And so you get this really pretty purple colored liquid, which looks a little different than the color of the cabbage. You remember the cabbage is kind of reddish, and here our liquid's kind of purple, and there's a reason for that. Okay, we'll just set that aside.
Your kitchen's going to be a wreck at the end of this.
Oh, yes, that's all right. It's part of the fun. All right, so we've got our indicator liquid, and then I've prepped a bunch of different liquids in advance. And you might notice they're all clear, but they're all different. Do you want to come help, Penny? Yeah, is this the fun part? All right, what we're gonna do is we're gonna add, I've got some old baby medicine syringes, which are really great for this. You can use a teaspoon if you want at home. We're just gonna open up these jars. We've got water, we've got white vinegar, we've got baking soda, water mixture, we've got lemon lime soda or pop, depending on where you're from, and we've got ammonia. And ammonia you want to be careful with because this one's actually a little bit hazardous. So if you've got kids working at home, you might want to skip the ammonia, or you might want to have the adults handle it because it is a little bit corrosive and it can cause some injuries. So it also is a little bit pungent. But I just use cleaning ammonia that you can get at the store. So now what we're going to do is we're going to add 1 squirt of this liquid to each of these containers. Before I do that, I think we have a poll. I want to ask you guys what you think is going to happen, right? Because making hypotheses is really important. So, right, if you have that poll, I don't know if it's live. There we go. What do you think is going to happen to the cabbage, to the different liquids as we add the cabbage liquid to it? Remember, the cabbage liquid's purple.
So the choices are they will all be purple like the cabbage liquid. They will be purple like the cabbage liquid, and they will all fizz. They will all change to be different colors. And then the fourth one, which seems to be popular, is they will change to be different colors, and some
will fizz. Is the part?
And some will fizz. Okay.
Okay.
That's definitely the most popular choice. We got 83% of the people think that's the right answer, and about 15% think that they will all change to be different colors.
All right. Well, let's see if you guys are right. So, Penny, you want to do the honors and start adding stuff to the? Can you reach? Add 1 squirt of liquid to each of the containers.
What is that?
1 squirt to each. All right, so the water, what color is that?
Purple.
Purple. Did it fizz?
No.
No.
First time go.
All right, go potty.
No, wait.
Well, we can wait.
No, I can't wait for you. I'm sorry. You can. There'll be more later. You can play later. All right, vinegar, different color. That one's nice pink color. Baking soda is a really pretty blue.
Is anything fizzing?
Oh, you know, the first time I did that fizzed, but it's not really fizzing at the moment. We'll see if something happens. The baking soda may or may not fizz. We've got the soda. That one's
Ooh, lots of fizzing. Holy cow.
It's also kind of going.
Uh-oh, stand back.
It's all right. There we go. And then we've got the ammonia. All right. So those of you who said some fizzing and All changing colors are correct. You might notice the pop is actually a gradient. It's kind of pink at the top, but not at the bottom, which is kind of interesting. And then we've got a range in colors, and I might just add a little bit more to each of these just to make it a little more vibrant. Kind of sad the baking soda didn't fizz. It did last time I did this.
Replication.
Replication. I know my replicates didn't work. All right, so if I were to ask you, how do we want to arrange these by color? What would you guys say?
Roy G. Biv.
Roy G. Biv, like the rainbow. I think that sounds great. So we're going to go with bright pink, light pink that's kind of got a little bit purplish to it. We got the water. Ooh,
Blue, indigo, violet.
Yeah, it's actually not a rainbow. Because you might be tempted to put the green in the middle, but actually we want them in this order where we're going from pink up to a green, and it's kind of a yellowish green. And so what we've just done is we've made something called an indicator, and we're going to talk a little bit more about the science of what's happening at the end. But before we do that, we're going to do an experiment, and we're going to do another hypothesis. So Penny, are you ready to help me? I've got 2 more liquids. Actually, before I do that, I might ask you, what do you think's different about each of these compounds?
The color.
The color.
And do here.
What do you know about vinegar versus water? What do you think, Penny?
Can you show them the color?
You want to show them a new color? All right, so you might notice that vinegar is a little bit more acidic than water. You might not think pop's acidic, but it actually is a little bit. Ammonia is something called a base, and we'll talk about what that means in a bit. So based on what happened here, and if I tell you that this indicator tells us how acidic something is, I want you guys to make a hypothesis about what color the lemon juice and the milk are going to turn when we add the indicator to them. So we have another poll.
Oh, another poll. What do you think is going to happen when we add the cabbage juice to the different test liquids?
You gotta wait, Penny.
A, they will all be purple like the cabbage liquid. No, second, this is, the new question is,
Yep.
what color do you think the lemon juice and milk will turn when we add the cabbage juice? Both turn purple, both turn pink, both turn blue. Lemon juice is pink, milk is blue. Lemon juice is blue, milk is pink. Lemon juice is pink and milk is purple. I have no idea, Rebecca.
All right, well, let's move these out of the way over here so that everybody can see really clearly.
But the popular choice seems to be lemon juice makes it pink and milk turns it blue.
All right, so blue is alkaline. So what that means is when you say that blue is an alkaline, whoops, pH, and wow, you're gonna be colorful. Okay, so, and then pink is acidic. So Penny, do you wanna add a squirt to each of our jars and see what happens? Push it in.
Turning pink.
Oh, it's turning pink. So those of you who said pink is correct for the lemon juice. Milk. We might need a second squirt. Can you do one more? It's opaque, so it's not going to take the color as well.
Such suspense.
Oh, it's really hard to tell. I don't know. Can you guys see? Maybe not.
Blue.
It's not blue.
It's not blue.
It's going to take a lot of
Kind of
indicators
murky.
to make it
Purple.
show.
It's turning purple?
It's kind of purple. But it's not as purple, I think, as the water. It's got a little bit of a pink cast to it, and it's a little hard to tell maybe from the video. But milk is actually slightly acidic, a little bit more acidic than water. And so you expect it to be somewhere in here. We put it in the right. And it is sort of somewhere in between. And it's a little easier to see when you're at home. It's not as nice in an opaque liquid. But those of you who said lemon juice is going to be pink are absolutely right. It's got a little bit of an orange hue just because the lemons are yellow, so it adds to that coloring. But that is the result of our experiment. So the last thing we've got are our balloons with our test liquids for our yeast to see how they responded to being grown in acid. acidic conditions versus non-acidic conditions. So I don't know, I don't remember if I had a poll. No, you're not allowed to drink vinegar.
He likes drinking vinegar juice.
I like drinking vinegar. Vinegar is her thing. So
Penny, I really like your t-shirt.
you did pick a good t-shirt for today.
Why?
I don't remember. Did I have a poll for this one? I'm trying to remember if I had one for the.
Last one.
Last poll you have is, what do you think will happen when we add bleach to one of the jars?
Oh, I forgot about that one. Okay, so what we're gonna do in the last one is we're gonna add a little bit of bleach. So bleach is alkaline, is an alkaline solution. And what I want to know is, what do you think is going to happen? We're going to add it to the vinegar. Oh, that's not it.
What do you think will happen when we add bleach to one of the jars?
Vinegar.
That's the wrong poll.
Vinegar.
It's got the wrong solution.
Vinegar. Vinegar.
Dear.
Still, people think it's going to make beer.
Those aren't the right answers to the question.
What do you think will happen when we add bleach to one of the jars? And so there's a bunch of choices, and 60% of the people think it'll make beer.
My bad.
Must be a lot of mechanical engineers in the audience.
All right, well, I lost that question. So the question was, we don't have the right answers to that poll. So we'll come back to that. I'll give you guys the right question for those answers in a minute. So what we're gonna do is add a little bit of bleach, and I'm gonna do this because I don't want you touching the bleach. And I need, where's the other syringe? There it is. So bleach is also alkaline, so you might suspect that it would turn it more towards purple. It might take a little bit.
White. More. White.
Wow.
But it didn't. So now this might make sense if you think about the fact that what do we use bleach for when we do laundry? We
Cleaning.
use it to make things white, right? And so the bleach actually acts a little bit differently. It doesn't interact with our indicator. It actually breaks it down so that it no longer shows the color. And so it does the same thing when you work with your clothes. And so we actually add this chemical. It reacts with the dye in our indicator and it breaks it down, just like you do when you do laundry and you add bleach to it, or when you put it on your hair. So it's a little bit different. Even though it's alkaline, it doesn't act the same way as our ammonia, which actually interacts with our indicator liquid.
Mom, if we put it on our head, it would change color. Right?
Yes, it would, and we're not going to try that. Okay, so we're going to come back and we're going to look at our bottles, and I'm going to post a poll for you guys with a hypothesis on what happens. So let me find it. So I want to ask you guys a question. Which of the balloons do you think is going to inflate, let's say, the most out of those three options?
And the choices are water, water plus vinegar, and vinegar.
Remember, it's a 50-50 mix of water and vinegar.
Oh, this is like being in class where nobody knows the answer. And they're all like, geez, it's like almost a neck and neck. Vinegar seems to be edging it out, but water is a close tie.
Mm. All right, we'll call that good.
Yeah, it looks like vinegar wins. Is it
Oh,
right?
it's pretty tied though. All right.
Oh boy.
So this has been working for about an hour. Excuse me.
They look pretty closely and similarly inflated. Oh, those are duds.
All right. So we've got our water here. We've got our water and vinegar, and then we've got our vinegar on the end. And what you can see is that yeast was not very happy having half the water replaced with vinegar. So you might get different results if you use a small amount of vinegar, because yeast doesn't mind it a little bit acidic, but very acidic, and it's not happy. It's not growing at all. And so this is one thing you might want to consider if you're making something like sourdough bread, right? Because sourdough bread actually has a lot of acid in it. And so a lot of times you have not just yeast in sourdough bread, you actually have that come from either yogurt that you might add to the sourdough or from the air. And so bacteria tends to be a lot.
We just lost you, Rebecca. Your sound is off.
No, it got muted.
We're back? Okay.
Yep, good.
Sorry, that was funny.
Sorry.
So
Munchkin.
never make bread with vinegar.
So be cautious about using too much vinegar, because just like adding too much salt or too much heat, you can make your yeast really unhappy and you could end up killing your bread. All
Very
right.
cool. Absolutely cool.
So those are the 2 experiments, and you can definitely try other things at home. Like just playing with these liquids is a lot of fun. You can try mixing them together. You can try adding them to different things in your house, like maybe make up a soap solution. You can try adding to that, or you can try adding to different things. Just be a little cautious if you're working with something that's a little bit corrosive, like ammonia and bleach. And one thing you might want to try doing if you do this at home is add some baking soda to some of these different containers and see what happens.
Mm-hmm.
That's a lot of fun. All right, those are the experiments. I had a little bit of a presentation on some of the science on what's happening. I know we're sort of out of time.
All right, so I think we're ready to go into Q&A about what's happening, and that might be a segue to show some of those slides.
Okay, sounds good.
So if we go to slide number 21, or around 21, the one right after your slides end, Rebecca. I wanted to kind of, first of all, thank Rebecca for inviting us to your kitchen and having, taking the time to prepare some science experiments we can do at home, and letting us learn a little bit about your passion.
Before you move on, I did put that someone mentioned in the open questions, never mix ammonia and bleach. You'll make chlorine gas. That is in the protocol under safety considerations, but I do need to tell you that right now before we move on. Never mix ammonia and bleach. It's very dangerous. Right. Thanks.
Good point. Very good point. All right, or Bryant, you could show slide 21, or Rebecca, whoever can toggle it up. So I want to just cue people in that next week, our webinar speaker is going to be Guy Meadows, who's going to be speaking about shipwrecks and underwater robots. And that's Monday, June 8th at 6 p.m. And Guy's, this is really interesting. This is under Lake Superior, where he finds shipwrecks and he images them using sound, I believe. And I also wanted to just gratefully acknowledge the session sponsorship by Mel and Gloria Visser. Mel is one of our chemical engineering graduates who graduated in 1959 with a BS in chemical engineering, and thanks so much, Mel. If you are interested in sponsoring a Husky Bites webinar, contact Bryant Weathers, and I don't think you can see the slide that I'm looking at, but his email is just BAWEATHE, Baweather, at mtu.edu. And all proceeds from these sponsorships are going in support to students in the Husky webinar. And so with that, we're ready to take Q&A. So go ahead and just enter a question, and we're going to handle them. And probably Rebecca will want to show some of the slides to explain what was happening, because I'm kind of curious, so to understand some of the basic chemistry that was going on, whether the, was the cabbage a base or an acid? I kind of got lost in the middle about what was going on. And I know that yeast reacts with sugar to make CO2, right? And so that was part of what was going on, but kind of getting a little bit of the background of the chemistry might be helpful.
Yeah, Brian, can you go? Brian has control of the screen. I don't know. Actually, I can control the screen if I get permission from, maybe not.
You should be a co-host.
Yeah, but he's sharing, so I don't.
Brian,
have,
can stop sharing.
Unshare and have you share, Rebecca?
I don't have this file open, unfortunately. So if you could go back a little bit, I'll tell you when to stop. Okay. So keep going. Keep going. All right. Keep going one more. All right, so what's actually happening here is we're dealing with a compound called a chromophore. And what we're dealing with is not really a chemical reaction when we're talking about the red cabbage liquid. What we're dealing with is a change in a chromophore that leads to a change in color. So you're probably very familiar with chromophores. You encounter them every time you're outside, every time you're preparing food. Chromophores include the color, the part of a compound that leads to its color. So chlorophyll is the compound that leads to the green color in plants. And the chromophore, the chlorophyll itself is not a chromophore, but that part that I've circled in green on this image is the chromophore part of that compound. And so that part is the part that actually is responsible for the green color that you see. If you go to the next slide, beta carotene is another example of a chromogenic compound, and the chromophore on here is the region that's in red. And beta carotenes are yellow or orange in color. And if you go to the next slide, this is the type of compound that we're working with, something called an anthocyanin. And so anthocyanins, you might notice they're all very different in terms of their chemical structure. I've given it for all of them. There are a lot of different kinds of anthocyanins. They all have this rough shape where the R groups are different functional groups that are on the sides. And so what happens is those functional groups actually gives you the differences in colors that you see, whether they range, they tend to be either red or blue or purple in color. And so what we have in the red cabbage is that's an anthocyanin. And oftentimes they have sugar groups off the sides as well. And so what's happening is that anthocyanin is actually one of the plant compounds used for defense. They actually interact really strongly with ultraviolet light, and they help prevent damage to the plant materials. And as humans, we really like the color. And so we've bred plants to actually have these really nice colors because they can make them naturally. Even though they may not necessarily need them in their fruiting structures. So what's actually happening? If you go to the next slide, anthocyanins are unique. They actually tell us how acidic a solution is. So the hydrogen ions that are in solution that tell us how acidic something is will interact with different parts of the anthocyanin molecule. And so the acidic form, those oxygen groups that are on the side of the anthocyanin will become protonated. The hydrogen really loves oxygen, and so it'll associate with those groups. And so when the hydrogen's on those groups, it changes it to a reddish color. When there's fewer hydrogen ions in solution, it's less acidic than that some of those oxygens don't have a hydrogen associated with them, and that changes the way the compound interacts with light, and it becomes more of a purple. And then as you have fewer and fewer hydrogen ions in solution, then those oxygen atoms have no hydrogens on them. It changes the way that compound interacts with light, and it becomes blue. And so anthocyanins are kind of are really fun compounds. And like I said, this works whether you're dealing with red cabbage or blueberries or purple carrots or any type of compound that actually has anthocyanins in it. It also means these are really tricky if you want to use them as a natural dye, because depending on how you might think, oh, I'm going to get a really great blue color from this, but it really depends on how acidic your shirt is that you're wearing, and you don't want it really acidic. So you're going to end up with a purple shirt, most likely, if you try to use these as a dye.
Interesting. I've been some of these vegetables and fruits also prefer acidic soils too, right? Or because I think blueberries prefer. Is that a factor in what's going on with their color? I think it must be.
It can be. The most famous plant that actually is related to pH are hydrangeas.
Yeah.
Hydrangeas are actually in reverse, and that's actually more complicated than what we're seeing here. And if anyone wants to hear about hydrangeas, I can talk about it, but it's a little bit more complicated.
A little off topic. All right, and so we've got a question from Imani Price saying, hello, will we get these slides in our emails, or will it be posted on the website? And we're happy to post the slides, right, Rebecca?
Yeah, absolutely.
Great. No, that'd be good. All right. And then Michelle Jarvie-Eggert says also never eat bleach. We won't, no. And I was puzzling in my head because I thought in my head when we add bleach to water, I convinced myself it formed hydrochloric acid and would be acidic, but instead it's more on the base side of things.
Oh gosh.
I don't know. I wasn't sure.
Bleach is considered alkaline.
Yeah.
It's got hypochlorite ions.
Shows my rusty chemical engineering brain. It's been a long time.
So Kay was asking about hydrangeas. So hydrangeas are actually, there are some, not all hydrangeas do this, but some hydrangeas will actually change color. They will be blue when in acidic soils, and they will be pink in more neutral soils. And the reason for that is not because of this reaction, what's happening here itself. What actually is happening is aluminum in the soil is really important. So you got to have some aluminum there. And the aluminum these compounds will chelate the aluminum, which means that they will non-covalently associate with the aluminum ions. And when that happens and it's under acidic conditions, it forms a blue compound. So when it's chelating aluminum, it's blue in acidic conditions, and it's pink in neutral conditions. And so that's what's happening in the hydrangeas.
Very interesting. All right, anybody can type a question into the polls. You just kind of you go down to the bottom, and there's a Q&A button, and you click on it, and you can type your question in. And Kay says, thank you.
You're welcome.
Well, and I definitely want to thank you again. I mean, that was quite a production to show for us, and it kind of really illustrates how even at distance we can be interactive, and we can kind of do experiments with some of the things we have at home. Oh, so Alice we're on the hydrangea theme. What about white hydrangeas?
I would assume that white hydrangeas don't have the anthocyanin at all. And so they're not expressing that color. And so you didn't even see it. Oh, chemical engineers. What do chemical engineers do?
What do chemical engineers do?
Oh, yes, I love this question. So if you go forward a few slides, I do have some slides on what chemical engineers do.
Well, and while you're getting to the slide, I will say chemical engineers can do anything.
Yes.
They can do anything.
Chemical engineers can do anything. And so chemical engineers, essentially, we take a knowledge of math, physics, chemistry, and biology, and we combine them to solve problems or fill needs. And so a lot of what chemical engineers do, we work pretty much anything that you use on a daily basis in your house that's not like a plant that you grow outside. There was a chemical engineer involved in making it somewhere. So we either made the plastics that go into your phone. There are chemical engineers who work on some superconductors. Chemical engineers help make all the consumer products, a lot of the processed foods, vinegar that you get in your house, beer and wine, anything that you pretty much eat that's processed even a little bit. Chemical engineers are part of that process. And so one of the things we do is we figure out how to take something like this, where we're doing something in a little vial, and we figure out how can we do this on a scale of thousands of tons. So chemical engineers take what chemists do in the lab. Some chemical engineers work in the lab too. And we figure out how to make this happen on a large basis so that it affects the most people. And so chemical engineers work in every field: pulp and paper, polymers, consumer products, petroleum industry, renewable energy, which is my field, a lot of places. And so it's great to be a chemical engineer because you take the same skills and you can apply them in any field. And so you basically find something that you're interested in and you can work there.
All right, we've got a couple of technical questions now. So would the vegetable experiment work with other vegetables like carrots or spinach?
No, because, well, purple carrots, yes, because they have anthocyanins, but orange carrots, probably not, and spinach, probably not, because they don't have the anthocyanins. You really need something that is red or purple, because the beta carotenes and the chlorophyll don't undergo this interaction with hydrogen ions that the anthocyanins do. So you really need something red, purple.
All right, and we have a question from Imani. Hello, did the yeast in the vinegar solution and the vinegar and water solution undergo an aerobic respiration reaction? Why wasn't the balloon inflated?
That's a great question. So aerobic respiration occurs when there's oxygen present, And even in aerobic respiration, that's what we do, right? As humans, we breathe in air, we eat sugars in our foods, our body converts those into energy and water and CO2, and so carbon dioxide, and we breathe that out. And so even under aerobic respiration conditions, the yeast should still be producing carbon dioxide. And so what's actually happening inside this reaction is the yeast start out aerobic, where there's some oxygen in this bottle, and they're consuming that. And they grow really fast when there's a lot of oxygen. But over time, what happens is they use up all the oxygen, and then there's none left, and then they undergo anaerobic, and they don't grow as much. They still make CO2. So under both conditions, they're making CO2. It's just one, they're making a little bit faster.
Ah, very good. All right, and so Stacy is an ME alumna, and she says, this has been fascinating, although I was not a fan of freshman chemistry. My 12-year-old daughter is watching too, and she's very interested in chemistry. She's loving it. Thanks.
Great, I'm glad. Chemistry is awesome. So is biology.
Amy met an actuary who has a chemical engineering degree, and I thought she was brilliant. Well, and I'll have a segue. The person down the hall, I'm a chemical engineer too. My bachelor's degree is in chemical engineering. I would get stuck on my homework problems. I would go down the hall. She would know the answer. I would kind of look at her answer, and I'd be like, oh, that's how you do it. And then I would go back down the hall, and so anyway, she was so brilliant. She ended up, she's already retired, and she manages other people's money. So she ended up, that's what she does. Chris asks, would beets work for this experiment?
Ooh, beets have a slightly different compound. I haven't tried beets. I think the color in beets might actually not be an anthocyanin. They have something, I think it's called betaine, and Sounds
like a good experiment to try.
Yeah, it sounds like a great experiment. I've got some beets that are growing in my garden. Maybe we'll give that a try later this summer, but I think that would be a great follow-up. If you got some beets, you can access to see if it would work. People definitely know the color forming compound in beets, what makes that red color. I think it's called betaine, and I don't know if it's an anthocyanin or not, so it'd be fun to check.
And Mel Visser asks, what makes the red, white, and blue colors in lupine?
Oh, great question, Mel. I would assume it's some type of anthocyanin, but like I said, there are some pigments that are not. And so I don't know. I'd have to look that up. I've never looked into lupins.
And on the roadway, as you're driving along Highway 41, you'll just see patches of them next to each. You'll see one blue and one, white one right next to each other. So I suspect it has something to do with just a mutation, in the lupine, but I don't know.
Yeah, I'm assuming they have slightly different compounds.
All right, we're gonna have to follow up with answers to some of these things. So Amy Monty wants to know, do you have a favorite organic molecule?
Oh, that's hard. I don't know. I'm a big fan of caffeine, but
that's organic, I think so. Noah mentions that chemical engineers play a crucial role in the renewable energy transition, both in materials and in alternate carbon sources. And that is for sure true. And Rebecca, I know some of your research is focused on creating biofuels from biomass, right?
Yes. So I didn't really talk about my research here. It's a bit different than what we covered here. I wanted something to be fun for everybody. So my research is really on looking at production of bio-based fuels and products. And so finding replacements for petroleum, because eventually it's going to be gone. And we need something that we can use in its place. And so I'm looking at things that are non-food based. And so you might know that we make a lot of ethanol that's fuel that comes from corn, and that's fine. However you might feel about that, it does have some benefits. But my goal is to try and make it out of things like grasses and trees. And so that's some of the work that we're doing in my lab, is coming up with a way that's better for the environment, that's able to replace something that we really need, and doing it in a way that's better.
Kudzu. Learn how to make it out of kudzu.
A lot of people are focused on doing stuff with some of these invasive plants. Here it's more, what's it called? It's
goatweed.
Goatweed. I saw you said you had an encounter with goatweed in your garden.
All right, Alice is just thanking you. My son is loving this. He is 9. Thank you so much.
Wonderful. Am I making
Michael?
Oh, go ahead.
So are you making biodiesel?
No, it's not biodiesel. So we're making In my lab, we're specifically making ethanol. And so ethanol is a compound that's in wine and beer, but it also can be used as a fuel. So we can burn it. And so actually most gasoline already has 10% ethanol in it. And so we're able to use it in most of our engines now, except for small engines. Don't use it in your small engines like your lawnmower. Not a good idea. But biodiesel is different. Biodiesel is made from oil. And so the stuff we're making is made from sugar. And so the oil-based diesel, that makes longer chain compounds that is more compatible with a diesel engine. And so biodiesel generally comes from oil-based crops, unless you're doing a different sort of method. And I saw David Schonard is on here. He's doing pyrolysis, and you can make biodiesel from pyrolysis as well. But it's a little bit of a different process.
Well, and Rebecca, you might mention, what was the class? I know I had to sign permission for you to do this. You were making brandy, right? Were you making brandy in one of your classes?
Yeah, we were going to make brandy. So I was teaching our bioprocess engineering lab, and bioprocess engineering is basically using microbes to make things. And so we can make a lot of stuff, and we didn't really get to go over their slides. But one of the things we make with microbes are we make bread, we make wine. And so investigating how to make wine. And Kira was in my class. She asked if I ever got to try it. No, it's still in the lab though. So it's still processing. Maybe it'll be in good shape by the time
it's aging.
It's aging, which is better for it. So.
And then Glenn has a comment saying chemical engineers are dominant in pharmaceuticals and in biopharmaceuticals. And so that's a good point, Glenn. I mean, and so chemical engineers play a vital role in, in combating this COVID pandemic. I mean, all these things have to be manufactured, and they're all mostly in a liquid form. Chemical engineers mostly work with liquids. That's kind of my recollection. Oh, and Mike was no, she doesn't make biodiesel, and that would probably mess up your car if she poured ethanol on it.
Oh, yeah, you got to be a little careful with biodiesel. The cold properties are really important. So when they're first getting into biodiesel production and using it to fill buses in Minneapolis, the cold properties weren't great, and it would actually gel in the engines. And so you absolutely don't want the biodiesel to gel in your engine. That's not a good, it's like putting, it's like suddenly having a vegetable like shortening in your car engine, which obviously isn't going to work very well. That said, I do have a student who's part of our consumer product manufacturing enterprise who I'm helping advise. He was in my alternative energy technology class, and he was really interested in biodiesel, and they're making it as part of his enterprise program. And so they weren't able to do their experiments because of the shutdown, but he's planning to start that up in the fall, assuming we're on campus. And they're actually going to use that in some of the lawn mowing equipment through grounds. So they've already worked that out. They're taking waste cooking oil from the dorms, and they're going to process it and use it to run some of the lawn equipment and see how that works.
Oh, that's terrific. That's terrific. Well, Rebecca, thank you so much for giving us your time at Family Dinner Hour and sharing your family with us, and sharing your learning with us, and having fun with us with experiments. It was really, really enjoyable to do this with you. Thank you.
You're welcome. This was
all
fun.
right. And I don't know if we're allowed to applaud, but sometimes at the bottom of your thing, there's an applaud button. I don't think we have it though. But anyway, applause for Dr. Rebecca Ong. Thank you so much. And we'll see you next week. If you're interested in sponsoring a Husky Bites webinar, send Bryant Withers an email. These are simple, kind of low-level, token scholarships. We're hoping for a total of $10,000 at the end of the summer to help award one more or two more Huskies a scholarship for the year. So thank you, everyone. See you next week for shipwrecks and underwater robots. Bye-bye.
Bye.
Thanks, team.